Hello, my name is Daniel Gustafson, and this is Lab 4. The purpose of this lab was to measure the distance dependence from a smaller magnet for the on-axis and off-axis magnetic fields on an observation location and compare it to computer models. I've also included my results from the lab, where my mu value was 4.1 amps per meter squared, and my N observed value was negative 2.642, which is fairly close to the theoretical value of negative 3. For the experimental setup, you want to make sure you have an app downloaded on your phone that has a magnetometer. This will allow you to get accurate measurements of the magnetic field produced from the magnet. From there, align your phone to where it is pointing in the same direction as magnetic north. Now, slide your phone up and down until you find the largest X value and smallest Y value. Place a piece of tape where the ruler is to indicate that the magnetic sensor is somewhere on this line. Rotate your phone 90 degrees and repeat. Once you have finished, the intersection between the two pieces of tape should be where the magnetic sensor is in your phone. For this experiment, we took different distance measurements based on the strength of the magnetic field. Here we did 20, 70, 120, 170, and 220 microteslas. With this data, we can plot them on a natural log graph. Our equation that best suits this graph will give us our N value, the slope, and the natural log of K value, which is the intercept. Using our values from the graph from our last slide, we can calculate the magnetic dipole moment, or mu. Since our magnet was parallel to our phone's magnetic sensor, we can use the parallel magnetic field formula. From there, we can group terms together and set them equal to an expression for the distance dependence, B equals Kr to the power of N. With some rearranging and plugging in calculated and universal values, our magnetic dipole moment comes out to be 4.1 amps per meter squared. For the next part of the lab, we will leave the magnet some distance away to where the magnetic field is 100 microteslas. From there, we move our phone up the same distance, again taking more measurements. When we input these measurements into the Excel spreadsheet that was provided, we get our magnetic field B. The last part of this lab is to write a code that will compute our off-axis computations. When we run this program, we will get our B field. As we can see, our model and observed B fields differ slightly. Some potential reasons for this can be other magnetic fields around my phone, such as the metal table I was using, my computer, or even the headphones I was wearing. Some others include my phone not being perfectly aligned with magnetic north, or some other discrepancy when finding the location of the magnetic sensor inside my phone. Finally, we have some post-lab questions that we can answer. If I hadn't oriented my experiment to compensate for magnetic north, all of my numbers would be off by a constant. We could calculate this constant by knowing where exactly I am using my latitude and longitude to calculate the magnetic field from Earth, then subtract that from my observations. But it is far easier just to zero out my phone by pointing it towards magnetic north. If I was to run the experiment again with two identical magnets joined together, I would expect the magnetic field produced by them to be stronger by almost a factor of 2. I would also assume that the data would be more clear, as the field would be stronger and more defined.